So we have a two-stage rocket, okay, and let's see, during the test, students observed the rocket is able to land at distance d 120 meters from the launching point as a whole. The rocket is on for a small time, beginning to provide initial velocity, but shuts down once it's in the air. Another trial that triggers separation mechanism somewhere in the air and observed M1 lands at distance 60 meters from the launching point. How far relative will M2 land? So here's the whole idea when we're doing the center of mass is before we have a motion and the center of mass is happening. Center of mass is somewhere in between them. Okay, we don't need to calculate it, but the center of mass, we'll say, lands at this point here. Now, even though they separate in here, even though they push on each other with the force, that's internal to the system, right? So the center of mass is still going to continue on that process from there to there. Okay, it's just now you have an object here and here, but it should still land at the same center of mass location. Okay, so we know the center of mass location ought to be D. And that ought to equal M1 x1 plus M2 x2 over M1 plus M2, because it's as though, even though they split apart, that's internal. Any forces they exert on each other is internal to the system, so the center of mass should still land in the same spot as before. There's no difference in the scenarios. So this is M1 times his position D plus M2, and this is what I'm trying to figure out what his location is, M1 plus M2. Now let's plug in some numbers here. We know D is 120. We know M1 is 3. And we know the little d that they landed here is 60, plus M2, which is 9, times his position, x2, divided by 3 plus 9. And then we want to solve for x2. So this is 12. 12 times that is going to be 1440. This is 180 plus 99x2. And then you can solve for x2 from here. I'm going to take that 1440, subtract 180, and then divide by 9. And I get 140 meters away.